Next up, we're going to hear from Dr. Steve Broglio. Dr. Broglio is a professor of kinesiology, neurology, and physical medicine and rehabilitation at the University of Michigan. He also serves as the concussion content lead here at the University of Michigan Injury Prevention Center, and he leads as the director of the Michigan Concussion Center and Neurotrauma Research Laboratory, where he both oversees center operations and conducts multidisciplinary research that's aimed at answering fundamental questions about concussion prevention, identification, diagnosis, management, and outcomes. So please join me in welcoming Dr. Broglio, and please remember to type all of your questions throughout the talk in the Q&A box.
Thank you. Appreciate the opportunity to speak today, in particular to the University of Michigan Injury Prevention Center for hosting their second annual virtual research symposium. I'm going to speak today a bit on using sensor technology to understand concussions. So just as a bit of context, the use of sensors, accelerometers specifically to evaluate concussions actually dates back to about 1975. And a study that was done in one collegiate football athlete, placing just a single axis accelerometer in the helmet. And then that was followed up nearly a quarter century later by some work done at University of Washington, again with an accelerometer system in the helmet. And you can see some of the basic metrics that were captured off of those two studies. What we later learned, however, was just measuring what's going on in the helmet doesn't really tell us what's going on with the head itself, or even more specifically with the brain. So that work was then kind of rolled out of the field and then taken into the lab. Some work by Andrew McIntosh doing some 2D motion capture analysis, and particularly with rugby athletes, starting to understand the thresholds, or at least what we presume to be the thresholds for concussion, and noting that they were occurring around 200 Gs of acceleration after the impact. This is an incredibly high level, and he did note in the paper that there was some measurement error in there, and then also, of course, that these are 2D analyses, these were 3D analyses. Probably what set off kind of the modern era of using sensors to evaluate for concussions was this work by Pellman, and this was the first of a series of papers done by the NFL. Some of which did not go over so well, some of the clinical outcomes, but his first two on biomechanics of injury were actually, they still hold the test of time. So in that study, they took a series of open field impacts resulting in concussion, and then they reconstructed them in the lab using hybrid 3 crash test dummies. And you can see a picture here that is from the paper. And they were able to evaluate what was happening at the center of mass of the head, to get this kind of average acceleration and linear and rotational acceleration that were occurring, that were causing concussion. And this 98G number, this is the number that we hear a lot in the literature, that this is quote unquote the threshold for concussion. And we're gonna take a deeper dive into that theory. So I've done some work in this space. We use a system called the head impact telemetry system. This is a six accelerometer system. They're all single axis, and they are, there's a proprietary algorithm that measures the center of mass. So with each impact, we can get the location of the impact, which you'll see in this red head form on the bottom right-hand corner, where every yellow arrow represents a single impact that an athlete took. And then we can also get the magnitude of the impact, and that's both in linear acceleration and in rotational acceleration. So in the head form picture, the tail on the arrow actually represents the magnitude of the impact. This is a wireless system. Data are captured in real time. It's transmitted to the sideline computer that you see. And the system's been validated against a hybrid 3 model in the lab. And you can see the kind of performance metrics there. The system has since come under some scrutiny as to really how accurate it actually is. But I would say for where we are in this space and the technology that's available, the head impact telemetry system has stood the test of time, although it does have some limitations. So let's talk about kind of head impact frequency, and I'm going to focus in on football, and this is certainly a limitation of all the research in this space. We're really limited to helmeted sports. The system is designed for football. So when we talk about soccer or maybe lacrosse or ice hockey, we don't have as great of an understanding of what's going on there. So I pulled some work that we've done in our group, primarily at the high school level, and then comparing it against youth athletes. And you can see this kind of range of impacts that's occurring at the various levels of play. If we drill down into the high school level, the average athlete takes about 650 impacts in a given season, which works out to about 50 impacts per week. And that's about 9, 10, 11 impacts per contact practice session, which is about twice a week, about 25 in a game. And then there's kind of a handful or a smattering of impacts that occur at various points, maybe a random non-contact day, they bump heads and that type of thing. But the big takeaway here is, the number of impacts can be as low as 45 in a given season, or as high as over 2,000 in a given season. So the range that these athletes are sustaining is actually quite significant. Obviously, we're interested in the number of impacts that people take. We're also interested in the magnitude of these impacts. How big are these impacts that people are sustaining? And if we look across the different levels of sport, the youth, the high school level, the college level, the average level of impact is actually about the same. They're all hovering in this kind of mid to low 20 G range, which is quite insignificant, actually. What gets more interesting, though, is if we start to drill down and we say, here's the median on this first column on the left-hand side, and we're splitting out across some different positions here, but then start looking at the highest level of magnitudes that these athletes are taking. When we start getting up into this top 1%, top 0.5% of all the impacts, really at the college level, we see this differentiation of the athletes where the magnitudes are getting substantially higher than what we're seeing across the younger players. So this idea of, they're bigger, faster, stronger, and those athletes are going on to play at the college level. We don't have good data at the pro level, but seeing that these magnitudes of impacts are increasing. So the question then becomes, with these top 0.5% or top maybe 1% of concussions, is there a threshold for concussion? Can we say once you cross a certain level, you're going to have a concussion? And this is just a series of papers that have been conducted, kind of making the suggestion about this smoking gun impact. You cross this level and then you have a concussion, and you'll kind of see that they're all hovering in this like 95 to 100 G range, depending on the level of play, but they're all pretty close to each other. And again, these are average linear accelerations that the concussions are occurring. So if we take this 100G, 98G idea, and we stack it up against these are some data that we have internally in high school athletes, we'll see that we had 260 impacts, 259 impacts that exceeded that, but only 9 concussions, and that resulted in 3.5% sensitivity, right? So the other 96.5% do not have concussions. There's another metric that's out there that has almost a regret. It's a weighted principal component analysis. And that same idea, we stacked that up against our data here. We had 150 impacts exceed that. That's at 6%. And then we did some internal analyses where we were able to get that level up to 21%. So the idea being is that, yes, we had a better metric or a better algorithm, if you will, to identify, but we're still missing 80% of the concussions that are, or we're only getting 20% of the concussions that are occurring over those thresholds. So the question then becomes, if it's not this smoking gun impact, and this is the kind of highest 1/3 of these impacts that we're seeing, we also have this kind of middle range of impacts that are also causing concussions. And then we have another set, or almost another 1/3 of the impacts at the bottom end that are also resulting in concussion, but they're not really high magnitude impacts. And you have some down here at the 50G range or maybe the 30G range, and they're still resulting in clinical signs and symptoms. So the question is, clearly we can have a single impact causes a concussion. Perhaps maybe the exposure of a person, how many smaller impacts they take on the day of injury, maybe that lowers that threshold for injury. Maybe that's a cumulative exposure over the season. And then this idea of maybe you've had multiple concussions and that results in a lower threshold. So we came up with this theory that we called a head impact density, a theory that may explain some of this. There is this idea that you have a single impact that crosses the threshold and that results in concussion. Or you could have multiple smaller concussions that build up over time, but it doesn't really change the threshold, but you have this kind of final blow that results in the concussion. Where we came up with the head impact density model was, yes, you have these smaller concussions, but each one of those may alter the threshold for injury. And as the time in between impacts increases, If it's short, then there's no time for the brain to recover. That threshold lowers. And if there's a higher amount of time, greater amount of time, that threshold goes back. But eventually, the reach at impact, let's say in this case, a 60G impact that has crossed the threshold that has now been lowered because of everything that comes before it. So these low levels of impact may cause some sort of subclinical shift in the ion shift in the brain that the brain is working to restore, but it's unable to get back up to that full high threshold before this kind of final impact happens to occur. So we did a study on this a few years ago to look into it, and we took a group of individuals that had that were concussed, and then we matched controls, looking at the final 20 impacts that resulted in concussion, and then we matched this final the magnitude of the final impact back to the control athlete. And what we see is that the linear accelerations, the cumulative linear accelerations between the two groups is actually the same. But really, if we look at kind of quote unquote the density of impacts, so the cumulative acceleration over the time at which they occurred, the concussed athletes have significantly higher exposure to G forces over a shorter amount of time relative to the control athletes. And so we're kind of leading to this idea that it's not the single impact, but perhaps it is this culmination of impacts over a short amount of time that is kind of altering this threshold for individuals. So thank you very much for your time. I need to give credit to our funders that support all the work we do. In particular, I want to give thanks to all the people that help do the work. They're the ones that are doing all the heavy lifting behind the scenes. I'm just a lucky one that gets to come and talk here today. And thank you again to the Injury Prevention Center for the opportunity to come and speak. And I'm happy to take some questions at this time. Thanks.
All right. Thank you, Dr. Broglio. That was a great presentation on the use of sensors and understanding sports-related concussions. We're in the live Q&A portion of this talk. I would encourage anyone to put any questions they have in the chat so that we can ask them here in real time. I do have a first question here that's come in. You talked a lot about sensors in football. I'm curious, are there sensors available for sports other than football?
Yeah, great question. And so really the sensor system that we've used the most and the one that I talked about in the presentation was initially adopted for hockey by the company that invented it. And it turned out to be an incredibly labor-intensive process. They actually had to cut holes in the hockey helmets by hand. And they, after talking to the owner actually about it, he said that, you know, we built 2 or 3 systems and we'll never build another one because it's just not cost effective for us. So what other groups have tried to do, other companies have tried to do is use mouth guard based. And then there's one company that actually had a sensor system that stuck behind the ear. This kind of skin based one didn't really pan out, I think, as people anticipated, but mouth guard based ones are becoming more and more prevalent in various forms. And obviously that can be used in any sport. So actually the advantage there is, the system we use is limited to helmeted, to football, of course, but even helmeted sports, if you kind of want to think a little broader, mouth guard based ones can be used really in any setting that the athlete's willing to wear it.
Great, yeah, that's helpful. You mentioned and talked a lot about the absence of really a concussion threshold. I wonder, sort of based on that, what you're feeling about utility in sensors.
I think that they still have utility. I mean, very much when we started, we thought, within a few years we'd identify this threshold and it would be this beautiful system. We'd never miss a concussion again. And as I mentioned, that just isn't the case. But the utility of the sensor system does allow us to track the individual that's taking a lot of hits. A lot of the systems track the location of the impact, so we can look at tackling technique in football in particular. And it does also notify clinical staff who took a big hit. And while that big hit may not be a yes, no, they have a concussion, at least it alerts you to that individual or an impact that you may not have seen if you were distracted on the sideline for some reason.
Great. And we do have one question in the chat that's coming up that, you talked a lot about sports-related concussion, but obviously there could be some applicability for these types of sensors in the military. Around head injuries. And I'm curious if you've given that much thought in your work or what your thoughts are about that.
We haven't. So we've used it at the service academies, the mouth guard based systems at the academies around some of their combatives and the boxing training that they do. I haven't used it in active duty personnel or even trainees for that matter around blast exposure, which may be where the question is kind of getting at. Other people have used it in that space, and that gets a little bit out of my area, but there's definitely some interest in it. It's a different type of sensor. It's a pressure sensor that goes in and not an accelerometer and a gyroscope. So it looked just a little bit different than the work that I've done.
Great, interesting. Thoughts on, so another question, thoughts on your relationship between head impact exposure and long-term clinical outcomes?
Great question, highly unresolved. I think, we're desperately grappling with this and trying to understand the relationship between whether it's concussion alone and the potential for long-term neurological deficits, concussion in combination with head impact exposure that doesn't cause overt clinical sense of symptoms, or whether it's just head impact exposure, period, that may or may not cause these issues. So there's a number of factors that play when we talk about long-term outcomes, and that's impact exposures, as the person asked, which is certainly, maybe kind of the spark that lights the powdered keg, if you will. But we have to talk about the genetic profile of the individual, their lifestyle, whether that's physical activity, socioeconomic status, environmental factors, just a whole host of things. And another project we're working on right now, we just got renewed our funding about a month ago. We're starting to track athletes after they've graduated college and from the military service academies in a prospective manner to understand who may end up with long-term problems, why they end up with it, to really try to be a little more nuanced in our understanding.
Good. So we'll look forward to future data on that. So I think that was the last question. So I really appreciate you coming to talk to the audience today. And it was a great talk about sports with concussion and sensors.
All right. Thanks, Pat. Good to see everybody, and appreciate the opportunity. Take care.
Awesome. Great. Thank you.